Welcome back, students. The topic that we are going to discuss today is the nucleus spin. This is a very important property of a nucleus. We have been talking about the other physical properties of a nucleus. Nucleus spin also forms an important property of a nucleus. So, what is nucleus spin? So, nucleus spin can be defined as the total angular momentum possessed by a nucleus. So this is a parameter which can be measured experimentally, and it is a characteristic of the nucleus of different elements. It's different for different elements. So it can be measured, as I said. So different nucleus has different angular momentum. How does this angular momentum of a nucleus arise? So we need to look into it. It basically comes from the angular momentum of the protons and the neutrons constituting the nucleus. So as we have already discussed, the nucleus is composed of the protons and the neutrons and the neutrons. So these protons and the neutrons together we call them the nucleons. So any nucleus, it is composed of the protons and the neutrons. These protons and the neutrons, they possesses an intrinsic spin angular momentum. So apart from that spin angular momentum, these protons and neutrons inside the nucleus, they move in a central force field, and they possess a kind of an orbital motion about the center of mass of the nucleon system. So these nucleons inside the nucleus, they have two kinds of orbital motion. One is the intrinsic spin angular momentum, and apart from the spin angular momentum, which is intrinsic to the nucleons, because of their spinning motion, they also have an orbital angular momentum. So the point we are trying to make here is the protons and the neutrons inside the nucleus, they possesses two kinds of angular momentum. One is the intrinsic spin angular momentum and also the orbital angular momentum due to the orbital motion of the protons and the neutrons about the center of mass of the nucleon system. So as a result, what happens is that the individual spin angular momentum and the orbital angular momentum of all the nucleons inside the nucleus, they add up, giving rise to the total angular momentum of the nucleus as a whole. So this total angular momentum of the nucleus is known as its nucleus spin. So if we look into the name nucleus spin, this actually is a kind of a misnomer. Misnomer means name, it seems to represent something else, but it represents something other than the name suggests. So nucleus spin, we may have a tendency of thinking it's only the spin angular momentum, but actually nucleus spin is a term which denotes the total angular momentum of the nucleus as a whole, and it is a resultant of all the individual spin angular momentum and the orbital angular momentum possessed by the nucleons inside the nucleus. And this nucleus spin is represented by the symbol I. And this nucleus spin is again quantized, and it can have a magnitude as per quantum mechanics root over I into I plus of 1 h cross. Also, with respect to an external magnetic field, when we say it's quantized, the Z component, let me say I have a magnetic field along the z axis. The z component of this nucleus field is quantized. Or in other words, the nucleus spin angular momentum vector, it can take only certain particular orientations with respect to an external magnetic field. Next, we'll talk about finding out the total angular momentum of a nucleus from the contribution due to the spin angular momentum and orbital angular momentum of the individual nucleons. So the question is how the individual spin and orbital angular momentum of all the nucleons present in the nucleus add up to give the total angular momentum of the nucleus. So there are two ways in which this adding up occurs. These are known as the LS and the JJ coupling scheme. So which coupling scheme will occur for a particular nucleus? It depends upon the strength of the interaction between the spin motion and the orbital motion of the nucleons in a nucleus. So in this LS coupling scheme, it can be represented as such. Individual spin where summation goes over all the nucleons in the nucleus. It will go from I to A, where A is the mass number, that is the total number of nucleons in the nucleus. So individual spins of all the spin angular momentum of all the nucleons, they add up to give me the total spin angular momentum. Individual orbital angular momentum of all the nucleons add up to give the total orbital angular momentum of all the nucleons. Then the orbital angular momentum of the nucleus is equal to the sum of L and S. This coupling scheme occurs when the strength of interaction between the spin motions of all the nucleons and the orbital motions of all the nucleons is stronger than the spin orbital interaction of the nucleons. Right? So what happens here is the interaction between the spin and spin motion of two nucleons will be stronger than the orbital spin interaction. So this gives rise to the LS coupling scheme. So the next coupling scheme we are talking about is the JJ coupling scheme. In this what happens? The individual orbital and spin angular momentum for nucleons, they add up to give me the total angular momentum for each individual nucleon. J1 is equal to L1 plus S1, J2 is equal to L2 plus S2 and so on. So finally, the total angular momentum of the nucleus will be summation over all the nucleons Ji, where I, summation over I, Ji, where I runs over all the nucleons. So this coupling scheme occurs when the strength of the spin and orbital motion, strength of the interaction between the spin and orbital motion is stronger than spin and orbital interaction. So what kind of interaction we are talking about is basically the electromagnetic interactions when the spin motion and orbital motion they occur for the nucleons in a nucleus. Now, what is the measured value of the total nucleus spin? Or what will be the total angular momentum of the nucleus? It depends upon whether the total number of nucleons, that is the mass number, is odd or even. Why it is so? It's because if we consider LS coupling, S is equal to summation over I SI. Now this SI can has a value of half H cross. So S can be either integral, it can have an integral value, or it can be half integral depending upon whether A is whether the total number of nucleons is even or odd. So total S will be integral if the total number of nucleons is even, and will be half integral if the total number of nucleons is Or similarly, the total orbital angular momentum is summation over Li. So Li can have values. It can be 0, 1, 2, etc. So the total orbital angular momentum can be either 0 or it will be an integral value. Therefore, when we consider the total angular momentum of the nucleus is equal to L plus of S, if A is even, then the nucleus value for I can be either, it will be integral values. It will be integral values. And if A is odd, what we'll observe is that I has usually half integral values. So, as we say, I will have integral values if A is even, that is the total number of nucleons is even, and I will be half integral if A is odd. However, it has been observed that the maximum measured value of I is equal to 9 by 2 H cross. Heavier nuclei among all the nucleus experimentally observed value maximum has been found to be 9 by 2 H cross. So this hints to the formation of pairs among the nucleons. So what happens in the pairs is that the individual orbital and spin angular momenta they cancel out, and the nucleons in the nucleus they form a core. This is known as core formation. So in the core has total I to be equal to 0. The core does not contribute anything. So if there is an unpaired nucleon, that unpaired nucleon determines the final spin of the nucleus as such. So this is all about nucleus spin. Later when we discuss about the shell model of the nucleus, we'll actually calculate or try to find out the spin of different nuclei.